This is our last and final episode on energy conservation. We just need to do this integral in multiple dimensions, that is in higher dimensions. This is what we seek to achieve. We are asking if we can express this integral as a change in the potential function u of r1 minus u of r2, as we did in one dimension. Can we do this, which is equal to the change in the kinetic energy? And the best we have done so far is that in 3D space, now if you have a location in the two-dimensional plane, xy plane, xy associated with this position is a height function, that if you can track this position to hit that height, you have a function u of xy. And let's just say you moved to a different location close to xy. Let's call that x plus delta x, y plus delta y. And associated with this new location is also another height. Let's call it u of x plus delta x, y plus delta y. And delta y, that is delta u, which is a change in the height function, is equal to, let's recall from the previous episode, is a partial derivative of the height function with respect to x times delta x plus a partial derivative of the height function with respect to y times delta y. In fact, plus the cross derivative, but that one is an infinitesimal, so it is very insignificant. That is the first important equation we need to keep. And from this change in the height function, we get that the cross derivatives are equal. So the y derivative, partial by the way, of the change in the height function with respect to x is equal to the x derivative, partial, of the height function change with respect to y. This is what we call the cross derivatives, and they are equal. Okay. So to give one example, let's say the height function, that is u of xy, is an explicit formula. Let's just say it depends on xy by this formula, say s squared y cubed. That is a height function. Okay. Let's see how we take partial derivatives. So what is the change in the height function with respect to, say, x? So partial derivative of this height function with respect to x is taken like this. If it is respect to x, you keep y as if it is a constant. You do nothing to y. It's like you taking a derivative that we have taken before, keeping this as a constant. So this is equal to, you differentiate x, but then you keep y a constant. So we have 2x y cubed. That's it. And the partial derivative of u with respect to y is equal to, keep x a constant. So you have differentiating y cubed, you have 3, keeping s squared a constant, y squared. That's it. So let's see if the cross derivatives are equal. So now this is the derivative of the height function with respect to x. Let's take the y derivative of that. Taking the y derivative of this, so we are trying to find d dy of du dx. That is equal to, taking the y derivative of this, we keep x a constant and every other constant. So this is equal to, taking the y derivative, 3 will fall down, so we have 6 x y squared. Then let's take the x derivative of this, that is this quantity. So partial derivative with respect to x of this quantity du dy is equal to, so we keep y a constant if it is respect to x. So we have differentiating s squared, we have 6x y squared. We can see clearly that the cross derivatives are equal. As we can see, we have 6x y squared, 6x y squared here. That's how to take partial derivatives. Now, we took the pain to treat this height function and to find the change in the height function, because this change in height function doesn't depend on how you move from this location to that location. Somebody can choose to move from this location and meander wherever he wants, however he wants it, to this location. Eventually, the change in the height between this location and that location that he will record will be the same as the change in height you will record if you move on a straight path. So the bottom line is a change in height is independent on how you move in the xy plane. So your floor, if you locate 2 points and then you start from the first point and move any way you want to second point, if you are tracking a height difference, the height it hits your roof, the difference in that height, if somebody also moves in a straight line, tracking a change in height is independent of the path you take. And you can immediately infer where we are driving the whole thing to. We are going to define some forces called conservative forces as a force that tracks a change in height. And if we're able to do that, then this integral can be done. Let's see why we are doing that. So let's just say, let's return to the xy plane. Now you have two locations, one here and then one there. You have a force moving an object on this trajectory to this point. Then you have the same force moving the object on this straight path. So this part 1, part 2. So you ask yourself, on which of these trajectories does the force do more work? Now, it is so clear that the object will experience more work, or the force will do more work on the part 1. Because on part 1, it tracks much distance compared to part 2. So the reason why this cannot be done in general is such that, you see, on part 1, the force does more work than part 2. So if you express it as a constant, that is u at r1 minus u at r2, if you express this integral as a constant, but then it turns out that it depends on the path getting different values for the work done, then you cannot express it as a constant. In fact, this is a constant. Let's just say it is 5 joules. The integral of a force dot a position vector is a constant 5 joules. That's what you are doing, expressing it as a change in potential function. But then you eventually find out that it depends on the path you take. If you take part 1, you get more work. It will be more than the 5 joules. If you take, say, part 2, it may be less than 5 joules. So how can you express it as a constant, given that it depends on the path? Unless maybe that force is such that it doesn't depend on the path. If you move on this path, if that force is a special force, you get a constant 5 joule. The same as if you move on, say, part 2. That is the kind of force we just want to investigate. We call them conservative forces. And we are defining those forces as a change in a height function. Because we eventually have discovered that a change in a height function is independent on the path you take. Somebody can choose to move from point 1 to point 2 on this path. But eventually, if we are both tracking a change in height, we get the same value. So, express, so in the 2D plane, the force is a vector, which is equal to Fx in the I direction plus Fy in the J direction. What if we express Fx as a change in a height function with respect to x, and then express Fy as a change in a height function with respect to y? So what if we write this force vector as a change in the partial derivative of a height function with respect to x, I, plus a partial derivative of a height function with respect to y, j? What if we do this? If we do this, then that means that this fx is tracking a height difference as you move in x, and you get the same value no matter which path you take, same as Fy. You see? So if we do this, then we can slot this equation back to the delta u. So the change in the height function in the 2D plane, okay, is going to be equal to, now we have expressed the partial derivative of the height function with respect to x as fx. So that will be fx times delta x plus fy times delta y. We have defined the special force as a change in the height function with respect to x plus a change in the height function with respect to y. And eventually, the work done by this force will be independent of the path taken. Now, this delta u is u2 minus u1. But in order to restore the analogy of the law of conservation of energy in 1D, which says that it is u1 minus u2, we introduce a negative sign. And to introduce that negative sign, we define fx as the negative partial derivative of u with respect to x, and then we define fy as the negative partial derivative of u with respect to y. So eventually the force vector is equal to negative into bracket partial derivative of u with respect to x, I, plus partial derivative of u with respect to y, j. So this negative is important. So we introduce a negative here, and we put this in bracket. Okay, so that we bring this negative here, so negative delta u will be equal to fx delta x plus fy delta y. See? Now, what is fx delta x plus fy delta y? It is a dot product of a force and a position vector. So negative delta u is equal to the dot product of a force vector and a position vector. And if we take the integral of both sides, we have the negative integral of delta u is equal to the integral of f dot dr. So that is from R1 to R2. Now, let's just say these are infinitesimals. So infinitesimal change in height, infinitesimal length or displacement in x, infinitesimal displacement in y. Now this integral, negative integral of delta u on a huge path, say from point 1 to point 2, eventually give us u1 minus u2. This on a very small path. Okay, so now you are tracking height from this point to that point. That height function is coming out of the blackboard. Okay, I mean the whiteboard, so to speak. Now, so moving from this point to that point, we can chop it into pieces. say you are taking this trajectory, you chop it. So between two infinitesimal displacements, you have a little change in height. Then you keep on tracking the height. So this delta u stands for an infinitesimal change in height. So that if you take the integral, it means you are doing it from this point to a huge or wide distance. Okay. So this will be equal to the integral of still the force vector dot dr from r1 to r2. So eventually we are able to do this because we have defined a force as a change in a height function with respect to x plus a change in a height function with respect to y. That's what we have done. And this negative sign we introduced was just to restore the fact that we needed u1 minus u2 and not u2 minus u1. So now we've been able to express in higher dimension that f dot dr from r1 to r2, which is equal to delta k, k2 minus k1, is equal to a height function at point 1 minus a height function at point 2. And we need this so much. Why do we need it? So if the force is defined from a change in a height function, which we call that force a conservative force. And if that force is a conservative force, this integral can be done once and for all. It is a height function at point 1 minus a height function at point 2. Remember, this is u of xy. U depends on xy. You see? So what is a conservative force? A conservative force is a force whose work done is independent of the path taken. But in technical terms, it is a force defined from a change in a height function. Okay? So if we're able to do this, then of course k1 plus u1 is equal to k2 plus u2. Okay. So in higher dimension, we're able to do this for conservative forces. But the good news is that nature is so kind. Now all the forces nature presents, apart from friction, in fact friction, a deep kind of analysis of friction is an average force. In a deeper sense, friction is an electromagnetic force. There are charges, repelling each other. Okay, but if you take it as a surface, a wide surface, then it is an average force of the electromagnetic force. But apart from friction, all the forces nature present to us, electromagnetic force, gravitational force, the strong force, the weak force, all these are conservative forces in the sense that they are defined from a change in the height function. Okay, so let's take on the higher dimensional energy conservation. Now we've now seen that a force is defined from a change in the height function. So that is equal to negative partial derivative of u with respect to x, I partial derivative of u with respect to y, j. That is what we call a conservative force. So fx is equal to that, and fy is equal to that. Okay. So the partial derivative of a height function with respect to x, the negative of that will be the x component of the force. And of course, the partial derivative of the height function with respect to y, negating that will be the y component of the force. What is the test that a force is conservative? Now, because it is defined from a height function, let's remember, for every height function in the 3D space, cross derivatives are equal. In other words, dx of du dy is equal to dy of du dx. This is for a height function in 3D space. Cross derivatives are equal. But a conservative force is defined from a change in a height function. So now let's watch out. Partial derivative of u with respect to y, we have defined that as r fy, negative by the way. the partial derivative of the highest function with respect to x, we have defined that as fx, negative by the way. So it turns out that the partial derivative of fy with respect to x is equal to the partial derivative of fx with respect to y. Now, because these are equal, the negative cancel out. So eventually we are saying that the partial derivative of the y component of the force with respect to x is equal to the partial derivative of the x component of the force with respect to y. That is a test for a conservative force. So if I give you a force like gravity, to test that it is conservative, you need to take the y derivative of the x component of the force and check if it is equal to the x derivative of the y component of the force. And all the forces nature presents us are conservative forces. Stay tuned. This is Popproof Advanced Physics class. We discuss classical physics and modern physics. Kindly subscribe, click on the notification bell, comment, share, and like my videos. In the next episode, we are talking about the dynamics of multiple objects. And we are starting with Kepler's law of planetary orbit. Stay tuned.